Okay.
I will.
Thanks a lot, Mark, for coming. It's very cool.
Okay, we've got the right screen up. Hi everyone. I am Mark. Somebody doesn't have. Oh, okay. I think we're good. So I'm a PhD candidate at Stanford University's Center for Computer Research in Music and Acoustics, known as CCRMA. My advisor is Julius Smith. If you ever Google DSP things, you've probably been on his website. I'm from Canada, did my undergrad in Montreal at McGill, where I met Gary Scavone and started doing some work with his lab in my undergrad, and that's how I kind of got introduced to this world of musical acoustics and kind of fell in love with it. I guess, yeah, so I studied guitar on my undergrad, and I'm, yeah, I guess primarily a guitarist, but now I play a lot of upright as well because nobody needs a guitarist, but everybody needs a bass player. And I recently started building and restoring some guitars, but I'm very, very much learning in that process, but enjoying it. So my research interests are kind of broadly measurements and like physical modeling of guitars, kind of with a focus on how that could be used in the luthiery process, but also in kind of processing instruments afterwards. Really interested in audio effects and studio recording and just anything to do with that. But also musical acoustics in general. But I focus on guitars just because I play guitar. So I'll give kind of the talk is a bit in two parts. One part is talking about measurement devices and setups, some of them just like the standard setups, and then some other things I've been working on. And then the second part is about more on the signal processing side of some research I worked on recently that I published in JASA last year, which also uses measurement techniques. So should kind of tie everything together. Also, yeah, please interrupt with questions or anything at any time. Happy to talk. And so first on the measurement setup. So at my lab we have kind of the standard PCB impact hammer that a lot of people have. That's the micro one. That's pretty nice. And then we have a single point Polytech laser vibrometer, which is very, very nice to have. And then, kind of other accelerometers, microphones, etc. We have, this is currently my measurement room with no treatment at all. The treatment is sitting out back, and we're just figuring out the best way to put it up. So that should be better soon, because up to now, microphone measurements in the room were kind of not very useful. Vibration measurements are still fine. So one thing I kind of have been working on is, with the micro hammer, you first start off doing it by hand and realize that that's pretty annoying to do. So then the next step, in Gary's lab, they had a pendulum, which would swing it slightly better. You pull it back and then drop it. It's a bit more repeatable, easier to avoid double hits of the hammer, which, you gotta avoid, causes comb filtering and everything. So then when I was there, I think I made just put a stepper motor on it to essentially pull the hammer back and release it, which, you could at least stand further away when you're taking your measurement and automate it with a button or a computer or something. And that helped. And then, but you could only measure things, since it was a pendulum, they had to be facing upward where the hammer could swing and hit it. Then, so a couple years ago, I visited Polytech, the maker of the laser vibrometer. They have one of their offices in California. And they had this nice automated hammer, which is actually just using the same PCB hammer, but with a 3D printed arm for it. And, it appears to be a stepper motor. I asked them how much it cost. They said a few $1,000s. That seemed like a lot of money for something that I could make. So then I made my own. So it's using the same hammer and just, some 3D printed adapters to hold it. And then a stepper motor, and it's all controlled by an Arduino, which you can control, you can program it to do whatever you want. You could send serial messages to trigger. You can vary kind of the speed and the of the hammer and the throwback, etc. To program it to get double hit or to not get double hits. And yeah, that works pretty nicely. This one it's on a big overly complicated mount that screws into the optical table, which is kind of adjustable in every direction, but annoying to use. So, I've got kind of various different types of mounts to hold it, however. But it's nice because it doesn't matter what direction that thing is mounted in, you can take measurements. Oh, yeah, just show. Yeah. And then I've also been working on some 3D printed inexpensive hammers. So we all know that PCB hammer, I think it's probably around $1,000 now, and then you need a conditioner, which is 500, or because it takes the IEPE power, so some other interface that provides that power. So pretty expensive, kind of not in the range for a lot of instrument makers. So I know Tom's here. He's also been working on impact, cheap impact hammers. So we'll talk soon, I guess, which I'm looking forward to. Mine, I've just been 3D printing a lot of stuff with it. And then, varying, I don't know how many there are now. They're all different, like a small tweak with each one. But I've mainly been using this Thorolab piezo stack, which is a tiny piezo sensor up in the corner here. They cost about $35, so pretty cheap. And they have the like hemispherical head, which is pretty nice for getting a single contact point. Here, I think this photo is, I've got another one on the other side, and I was using it to measure the speed of sound across the wood, with just looking at the time delay between the wavefronts, etc. Yeah, so there's that one, yeah, just on a pendulum there, but got other ones on a stepper motor. So another thing that when I was at Polytech, the main reason I went there was to they offered me to come visit and use their scanning vibrometer, which we don't have, but I wanted one. So that was really nice. You put your device up. Some of you may have them in your lab, and then you can set what points you want to scan over and view mode shapes, etc. But they're pretty expensive. I think they said around $120,000 maybe, and pretty large and complicated. And I wish I had one, but I don't. But yeah, so some of the mode shapes you can measure here is just the like 100 hertz mode of a guitar mounted there. Another really nice thing, which I never thought about before or hadn't seen before, which is measuring the actual plotting the time domain motion. So here in the blue circle spot is where it's getting struck in the back with the impact hammer, and you can see the wavefront start to propagate. And note how much faster it goes along the grain than across the grain. Which is so this top was it's a sinker redwood, so it's a piece of redwood that they cut down in sometime in the 1800s in California, and then used to ship them down the river, and something like half them didn't make the trip and sunk into the river. And now you can't try not to cut down the old growth redwoods anymore, but you can find these old logs that were cut 150 years ago at the bottom of the river and pull them up. But they changed a lot. So this is redwood, but it's brown now, like a very deep brown. They have different colors based on the minerals that were in the water. And then, so this one is from some of the luthiers I work with. They said it was, too floppy to be actually used in a guitar. It bends super easily. And then, so it's looking at kind of the stiffness in each directions. And yeah, the speed of sound in the along the grain is like 5 times as high as across the grain, which you see in the wavefront here as well, which is really, I don't know, it's really nice. So anyway, I wanted to be able to make some measurements like this of my own. And you could do it by like the roving hammer or the roving laser technique, where you set up a grid and then take all these measurements individually, but that just seemed very tedious, and I have never wanted to do that personally. So I have been kind of thinking about making my own sort of scanning vibrometer for a while. originally thought about getting like a 3D printer type grid, like an XY grid, and then moving the vibrometer or the hammer. But then I was talking to some people and they said to just get a laser galvo. So that's what I did. Um, and this is my, the first attempts at my setup with all the circuit boards just loosely set out. I'm kind of still working on this a lot, but so here's in the bottom right corner is the laser galvo. So it's essentially two mirrors that rotate and redirect the laser beam, so I can scan over a grid now. And it's all very inexpensive. This one is like, I think it was like just over $100. I should maybe get a slightly better one eventually, but it's seeming to work okay for now. And it's all controlled by a teensy microcontroller. This one particularly because it has 12-bit analog outputs, which I'm using to control the laser system, the mirrors. And here's just, showing nothing complicated, but showing the laser moving across whatever grid you program it to. And yes, and for all this, I was just like 3D printing hardware for mounting and making circuit boards, and kind of definitely still a work in progress, but it's looking, it's fun. So here are some mode shapes that I measured with this system. They're pretty rough and like there's not a lot of processing on it, but they're there. Need to do more cleaning up on that and signal processing. Also, some things just at the moment, it's not doing anything to detect a double hit. It's just setting it to take the measurement across the grid, but need to program some more stuff in to, get rid of bad measurements, retake them, etc. So that's the actual current setup with still wires hanging off everywhere, which isn't very nice, but it's fine. So anyway, updated the laser for $150 to scan. So another thing I've been working on, I think I mentioned to Sebastian earlier, which is trying to measure tone woods. And we all know it's a bit iffy. It's not the easiest thing to do. And if you look up values for material parameters in a textbook, they're, based on some measurements at some point of some samples that you don't know what they are. So it might give you a broad idea, but it's not super helpful for actually building an instrument. So I've been working on a device with some luthiers I collaborate with at the Santa Cruz Guitar Company. They're about a half or an hour drive south of me, but on the coast in a very nice area. This is their, about, I don't know, a third of their wood stash, which is nice. With guitars, you get to work with a lot more, much wider variance in the wood than with violins, which is cool. So here is the actual device I have. I think it's sitting back there. So there's some things we wanted to try to measure. The dimensions of the board, the mass density, the stiffness along and across the grain, radiation coefficient just calculated from those parameters. And then also to get some more of the just vibration properties, kind of the overall like EQ balance, and then also the decay. And wanted to also had some constraints of wanted it to be very easy, like completely self-contained, so that I don't have to be there taking all these measurements. I can leave it in the guitar shop, and then they can make the measurements as they need to take out wood, or as a stack of tops come in, they can take measurements after they age for a bit and dry to acclimate to their shop, and then all the data is uploaded to the cloud so I can see it and use it as well. And then we can kind of start to go through some statistical analysis after and see what the differences are. And also trying to keep the cost down. I think the total cost is maybe $150, $200. No, the most expensive thing I think is a camera on top, which is like $80. It's just nothing. Yeah. Just one prototype here. So how it's measuring everything. So it's all constructed out of this 80/20 fabrication material. It's just general, you can construct it. And then a bunch of kind of 3D printing for all the custom parts I needed, and some laser cutting. And then it's all controlled by one of the same teensy processors, which is it's kind of a slightly more high-powered Arduino, but it's this nice audio shield that you can use with it, which has a 16-bit 44.1 two-channel DAC and AVC. So everything here is actually, it's taking all of the sensor data in as well as the audio data from the vibration sensors. And then it's just connected with one USB connection to a computer, which is then sending serial messages back to control the stepper motor and everything else. And it's all, yeah, written in Python and Arduino, hoping to kind of eventually release it all. I'm planning to submit this to the Vienna talk and talk about it there, and write an actual paper about it at some point, and then clean everything up and document it better in case anyone else is interested. So yeah, so the mass is so this is where the actual tone wood is mounted, and it's all mounted on a load cell. So it's, these are things you could do otherwise very easily, just putting it on a scale, but I just wanted it to be self-contained. So it's doing that. This foam, I'll talk about that in a second, is how it's actually mounted. The length and the width, this is kind of probably the most ridiculous thing. You could use a measuring tape, but instead I'm using a camera and image processing and edge detection. I don't know why, because it's fun, it's easier. You don't have to think about it measuring it, and you take a nice picture of it, which you save for later to keep track of the samples you're measuring. So yeah, just this small USB 4K camera overhead takes a picture, it has edge detection. So it's mounted on, like, if you put something black behind it, it helps a lot with the edge detection, which I found out about. So notably, this is, for a rectangular board, you can usually measure the dimensions, but a lot of the wood that they get is not rectangular. So if you wanted to expand it to, whatever shape the wood comes in, you couldn't do that with just a measuring tape. Well, you could, it'd be very tedious, but with image detection, you could make a geometry and then eventually kind of, mesh it, and then do some finite element and then try to determine your parameters better. So trying to keep it open for the future. Thickness is measured with a Hall effect sensor and a magnet. So there's this little clip that goes on, which has a magnet on one side and a Hall effect sensor on the other side, which is measuring the magnetic field strength. So it's going to vary with the distance, and that's just calibrated with various thicknesses to measure it. Since it's a guitar, which is nice, not like a violin wedge where you have variable thickness. And then, yeah, so the impact hammer, similar type thing here. It's a stepper motor with a 3D printed arm and another one of the piezo sensors in the tip. And then, yeah, it's actually, it's at the moment it's programmed to take 5 measurements, and then afterwards you can do a bit of statistics on them and stuff like that, throw out any outliers, etc. And then the vibration response of the actual board is measured with in the same clip with the Hall effect sensor, there's also one of the piezo heads, which is then clipped on. And yeah, it's then, afterwards we're correcting out the hammer signal. It's not quite the admittance because this isn't velocity, but you're at least correcting for the amplitude of the strike when you're doing that, kind of like when you look, which is important for the equalization balance, etc., when comparing different measurements. And yeah, placing it on the location on the board is, I chose to go kind of in the middle, near the edge. So you're not at a node of either of the first 2 flexural modes, this direction, that one, like the tangential and longitudinal. And it made sense with the device, and I think the main thing is keeping it consistent. Yeah, so the wood mounting is mounted on this foam, which is made in a way that it's easy to set on the piece of wood and adjust it, that you want the foam supports to be at the nodes of the longitudinal and tangential flexural modes, which are, I think, 0.224 of from the end of the length, the ratio. Um, and then, so from that, I'm just using the impulse excitation technique method to approximate the Young's modulus in either of those directions. So it's essentially, kind of an approximation of the Young's modulus from the frequency of the vibration mode and the length, width, thickness, mass. So here's just like one example of a measurement here, and you see other vibration modes, but these two are the most prominent because those are where we're mounting it at the nodes, whereas for all the other modes where the mounting is at some antinode, likely. So we get the highest peaks here, which are then doing peak picking to get the frequency of, and then the radiation coefficient in the standard way. And then the equalization just picked some frequency ranges corresponding roughly to low, mid, and high. You could, fit these, you could fit all the modes of the measurement, but that's probably too much information to be useful to a luthier. I'm also like saving all the data so I can do this all afterwards, but to give out the information. So it's just band passing them and checking the signal energy in each of those bands. And same with the decay, same band pass filters in those ranges. And then, fitting the slope in the linear or in a log space to get the T60 as a kind of easily understandable metric of decay. So here's just a few examples of that process with some woods. Moon spruce, I think it's like a European spruce, I think from the Alps, redwood, and then Adirondack spruce, which is spruce from the Northeast United States, common on old Martin guitars. So you can, notably that the stiffnesses are very, as kind of one would expect, redwood would be low or less stiff than, a high alpine spruce. And then you get, the actual, it's pretty interesting in the low, like the EQ and the T60 as well, just for comparison. Some of the measurements are getting messed up at the moment. My hammer is clipping occasionally, and I just need to make some signal conditioning to not clip. But when it does, since we're compensating for the hammer signal, it messes everything up in that for the decay and the amplitude. And these are just the pictures that were grabbed from those measurements and saved. So yeah, the status of it, is still working on it. Kind of go in once a week and check and try different things and see what needs to be worked on. But the whole process is here. Just to show like how self-contained it is, you run the script, you enter like the wood number and the wood type, and then it will then takes the hammer down and until it hits the wood and then backs up a little bit to the right spot, and then takes 5 measurements here. And then it just asks you if something went wrong with the measurement. If not, save it. And then everything's uploaded to the cloud. And then also it prints a sticker out with all the parameters that are calculated so that you can then label the wood to know so you don't mix it up later. All pretty self-contained, takes 30 seconds or something like that. Just nice. Yeah. All right, on to the second part now, which is pretty different. Should maybe pause any questions on the first part, or I can keep powering through until the end.
I love the printing label. That will solve so much of my headaches.
Yeah. I don't know. It's very satisfying too when it prints and then you just take the sticker off and put it on.
Yeah.
And yeah.
One question with the laser: how precise? Like, can you repeat the measurements in the same position, or there is a?
Of the scanning one.
Uh-huh.
Yeah, I haven't tested exactly, but I think it's going to be pretty precise. So it's a 12-bit controller, so it's 4,096 points in each direction that you could scan over. And the mirror system is pretty precise.
Okay.
I haven't checked exactly, and it's a cheap mirror system, so I'm not exactly sure. Um, but I don't have any reason to believe otherwise at the moment. Because like you can tell, like if you change, the voltage you're outputting by a little bit, you can see the laser move and you can move it back. But I haven't checked exactly, yeah, how repeatable that is.
Any
Yeah.
other questions of the first part? You want just unmute yourself and go for it. Well, just you can continue.
Okay, sure. I also should just mention for the so was there a question? Okay, so yeah, for the material parameter estimation, those are good first estimates of two of the Young's modulus, but there's lots of other parameters, which the work your group has been doing is really good, and I'm kind of working on also, from this you have the dimensions. You can make a finite element model, which I'm working on otherwise, and then might end up going the same route. Going to try a few other things as well that I've been thinking about. But to try to get a better estimate of those parameters based on comparing the vibration response to that generated by a modal analysis of a finite element model, and also get an estimate of the other parameters. Yeah, so I'll continue. I'm a bit late on time, so I'll speed up a bit. So this is paper I recently published in JASA. The idea is to process an electric guitar to sound like an acoustic guitar and make it parameterizable. So why might you want to do this? Just audio effects. You want your guitar to sound like a different guitar. That's a pretty common thing. There's lots of, there's pedals and things that try to make electric guitars sound like acoustic guitars. And I don't know exactly what, they're all doing different things, but my assumption is it's something like they're doing convolution with an impulse response of an acoustic guitar or some filter bank method, but they're not doing anything to change the decay. Or if the most I've seen is like like a single band like downward expander to change the envelope of the decay. But I'm trying to match the decay and the equalization of an acoustic guitar in like in a frequency dependent way to actually like match the differences, which hopefully become more clear later on. And one of my main motivations is to use this to actually study guitar design. So the way to, previously you could, generate an impulse response or like an admittance of an instrument, or take one that you had from a measurement and then vary it, and then do synthesis and then see how, if I change this mode by 5 hertz, like how does it perceptually change? But it's all synthesis, which it can sound really good, but the playing parameters are really difficult to get it to sound kind of realistic. But here it's meant to process on a real-time instrument. So you're actually processing the output of the electric guitar. So you have the playing parameters for free from the guitar playing. And then you're just changing the sound to kind of mimic that synthesis change. So you could, yeah, want to use it to study how you could vary an instrument and how that will change the perception. So the motivation is kind of, not sure if you're familiar with like the digital waveguide model. It's essentially, you have the left going and the right going wave, like Helmholtz wave corners from the string as it's plucked. One kind of traveling towards the bridge and one traveling towards the nut, and then they reflect with some scattering and come back and interfere. So here on the bottom is the block diagram of that. So you have some delay line traveling to the right, which then hits this scattering filter at the end. Some energy is transferred through to the bridge and then radiated as sound, and then some energy is transferred back into the string and then hits the nut here, which I'm just assuming is a rigid termination. I did some work before, and it's not really a rigid termination. You see kind of the neck modes there, but those don't really affect the sound, more so the decay. But they're just ignored for now because it's also complicated because it changes at every fret. And just, yes, what this looks like in a simulation is, here's your two kind of, if you had just two pulses going in and then the output here, or if they're decaying. So that So this is with just a scale factor gain, but what we actually have is the scattering filter or scattering junction there is frequency dependent and depends on the admittance of the instrument. So that's going to change. So actually this, every time the kind of the wave hits here, it should have this filter applied to it, which is kind of, you could think of it's being like recursively applied. So if a pulse keeps traveling through here, say if it travels through 100 times, which is 100 what trips of the wavelength through, which you get in your decay, you're actually applying that filter 100 times iteratively, which works really well in a feedback system in synthesis, but that is difficult to do in real-time processing. So my approach to do that was, first you need to know when you actually pluck a string so that you can reset this filter. So I'm just doing transient detection for that to detect string plucks. Should also mention it's on a hexaphonic guitar I'm doing the processing. So actually this filter is going to be different for each string because it depends on the relative impedance of the bridge and the impedance of the string. So it's going to be a different filter for each string. So processing them independently. Then you need to know the pitch of that string so you can know how often to update this filter. And then you need a measurement of the both the guitar's bridge admittance. So here's kind of the block diagrams. You have 6 of these processes running on each string: transient detection, pitch detection, and then resetting the filter. And then at every sample, this filter is running. And then you can also have a radiation filter to mimic the sound to a microphone. Transient detection, it's just, I'm doing like an RMS detection and a peak detection, and then detecting when they cross, and then just detecting that as a new note. This is kind of standard like compressor based architecture. It's not the main point of the processing. It's just kind of a tool that was necessary. Same with the pitch detection. Just pretty much using the pitch function in MATLAB, or was at the start, but there's lots of other more complicated algorithms, but this was working reasonable at the moment. But the end of the actual processing. So this is your like the reflectance filter. So this is the filter that the string pulse is seeing at the bridge, where RB is the bridge impedance, which is so the inverse of the admittance, and RS is the string impedance, which is calculated from the tension and the linear mass density of the string. And then, so from that we have, so if we had our admittance, sorry, I'm changing between them, but I don't know, it is the way I think, at least. So our admittance can be modeled as a parallel bank of resonant peaking filters, where it's taken from a measurement, or it can be generically made, where you have the center frequencies, the damping, and the amplitude of each of the modes, and then it's just this bank. So then when you plug that in, you have your reflectance filter comes out to this other second order equation, or bank of second order filters, which is more like notch filters now. And then, so also, since we have an electric guitar and an acoustic guitar, we want to do a correction on them. So we want to impart the scattering of the acoustic guitar and take away the scattering of the electric guitar, which we can do as by division in the frequency domain. So we'd have this scattering filter fit to the electric guitar and one to the acoustic guitar. And then to actually apply it, turns out to be a very, because we were all dealing with infinite impulse response filters before, which is nice because they're low order and parameterizable. But to design a increasing order IAR filter and try to keep it low order seemed to be a very tough signal processing problem, which I haven't found a good approximate for. I could get it in certain ranges, but what ended up working better is switching back to FIR at this point, and then using a warped FIR structure to focus on the low frequencies. And it's a pretty reasonably low order FIR. It's using 1024 taps maybe. But then you can easily iterate the filter, or by increasing the exponent on the filter and then taking it back. And then should note, so that's all assuming we have like a velocity force admittance relationship at the bridge, which is what you need for the scattering. But then the sound is actually, radiated in some complex radiation function. So at the moment, you could like model the radiation filter by taking the same measurement with a microphone somewhere, and then using the same modes to create a filter, but changing the complex gain, which is going to affect your amplitudes and your relative phase of that. And that's just implemented with this first order filter, which preserves the phase information. Then you take the real of the signal at the end. And the thing to note was that the pickup had to be integrated because I wanted to measure proportional to the force. And also it's not flat, which I need to just put in some correction for later to correct it, because as you'll hear in the samples later, there's some ringing and stuff, which is I think just due to the pickup, and I need to correct for that. And I just did this digitally with an integration filter. So in a test case here, I used, a solid body electric guitar, Les Paul, super high bridge impedance because it's a giant chunk of maple and mahogany. It's not vibrating very much. And then just one of my guitars that I had around. And so here's the hexaphonic bridge pickup. Yeah, use the same set of strings. You could factor in different strings, but just at the start, I used the same ones. One note is that the scale length is different, which I did not account for, but just one thing for future work. So on the measurements, here's the guitar mounted impact hammer, laser vibrometer, standard type of admittance measurement. There's a microphone. There's one here, kind of at like a standard recording position and by the 12th fret of the neck. I think there's probably one somewhere else as well. There's actually two here. There might be a couple more, which are used for the radiation filter. So here are the admittance measurements. The black is the measurement, and the red is a modal fit to it. So fitting the frequencies, damping, and amplitude, and noting that it's going to be maintaining a stable filter by having only real gains, which keeps your phase in between plus or minus pi/2. So for the Martin, I used 50 modes, and for the Les Paul, the solid body guitar, where the admittance is much less active. It's much lower, higher mode frequencies, generally corresponding to like the neck motion. There were only 11 modes fit. So here are the actual reflectance filters for I think this is the low E string. And they'll look the same for each one, generally for each string, but this amplitude scale will be changed because you have that constant string impedance in. So the acoustic one is in blue, which you can't really see. The electric is in orange, and if we combine them, we see that the acoustic, it almost follows the acoustic admittance, except in the parts where the electric guitar has these positive admittance swings. Positive reflectance in the inverse, which, if our measurements match the instrument perfectly, because this is, whenever it's above 1, it's an unstable filter, so we could have exponential increase here. If we're matching the instrument perfectly, then it would be fine because the instrument is decaying and we are applying an exponential, so it should remain stable. But there's measurement error, so that's probably not the case, and it's probably going to go unstable. So I ended up just putting limits on this to make sure it doesn't go above 1. So the purple is the combined with the limits, and then just showing the worked FIR structure of how this is implemented. The blue is that original filter. The orange is if just using a 2048 tap filter, and then the yellow is using a warped FIR filter, which is essentially kind of zooming in on the low frequencies, and fits much better. And then here's just a radiation filter. So it's the same mode frequencies and damping, but different amplitudes. And here's some examples. We'll see how they sound. So here's a low E just on the pickup. Note that the sustain is like, it's like 16 seconds long or something like that. So here, that was just the pickup signal. Here's the integrated pickup signal. Here's the pickup signal. So if you added just the like convolution with the radiation filter. So we're starting to sound more like an acoustic guitar. And here's the fully processed version. So note the frequency dependent decay is changed. And so here for reference, you're never going to sound the exact same. This is, a different pluck, etc. Is the acoustic guitar. But note the decay matches much more closely, and the overall equalization is kind of there. It's not perfect. But here on the left is showing so here's it's the T60 of the first 10 harmonics of that pluck, with the blue being the pickup, and the yellow is the acoustic, and the orange is the processed pickup. So it matches like relatively pretty closely. Oh no. Sorry. Okay, now I know that happens. Okay. So here, same kind of thing, just with a different string. So I'll go through them again. So that's the highest frequency, or that's just the electric guitar. That's wait. Oh, sorry, that's the electric guitar. These are not playing in the correct order, sorry. That's the integrated electric guitar. Electric guitar with the body filter. Oh. So that's the fully processed one. And then the acoustic guitar. So relatively close, same kind of thing with the harmonics. And then just some playing examples. Here's a picture of my cat in a guitar case. So the acoustic guitar. So here's the integrated electric pickup. Here's the electric guitar pickup with the body filter. And then here's the fully processed. So it's not perfect, but it's a lot closer. There's still some ringing, which I just need to sort out. Oh no. Sorry. And then another fun thing that you can do is change all the modes and see how it sounds. So here's just all the mode frequencies are scaled by a factor of 1.5. Here's the original again. And then here's the scaled version. So yeah, sounds kind of like a mandolin, maybe. So yeah, future, some things to do, figure out the bugs, figure out how to get my slides to not autoplay the audio when I move on. And then yeah, improve the pickups a bit, and then actually use it to study guitars like I was have been kind of the reason I wanted to do it in the first place. So yeah, thank you. Any questions or comments? Happy to talk now. Yeah, thanks for inviting me.
Thanks a lot. Love it.
Yeah. Mark, I have a comment, if I might. It was a great, great talk. A lot of great work you're doing there. I just wanted to share something, if I could share my screen real quick, related to the device that you're building for Santa
Now
Cruz.
you should be able to.
Okay.
Yeah.
Let's see.
Who is this is speaking right now?
This is Tom Nania.
Let's see. Tom. Okay, that's what I thought. Okay.
Let's see. So this is I just thought you'd get a kick out of this. Something I worked on a couple of years ago for some guitar makers in Michigan, but related to the device that you were working on.
Yeah. So what's going? Okay.
Let's see. Trying to get this to play. It's basically a automated scanner. It's kind of like the idea behind it was like a credit card machine where you'd slide a piece of wood in, it drops it on an acoustic test bed, and then takes the measurements and spits it out with a label. I'm just trying to get the video to play. But
nice.
Yeah, it's just kind of fun. Yeah, it's not giving me.
I think you need to select the option when you share. So stop sharing, select share again, and then you need to automatically optimize for motion and video. I think we lost Tom.
It may have asked to install a thing beforehand and then drop out and come back. I know it did that the first time I did that, so maybe we'll get Tom back soon.
Okay, yeah, well, in the meantime, any other question?
Maybe I can just comment on the first section.
Sure.
I liked it quite a lot. I mean, it's quite the opposite that we're doing, because we have these laser adopter vibrometers here, and like taking these hundreds of $1,000 equipment to make nice measurements. And I liked it quite a lot that you can achieve like quite nice results with kind of affordable equipment. It's quite the opposite direction we're going here, but it might head into something that's really usable by guitar makers, which is a nice thing, because for us it's working very well, but no luthier ever will be able to use it because it's just way too expensive.
Exactly. And generally, you can't quite get the same quality of measurements, but you can get, close, you can get usable measurements for a luthier, and they often don't need the same quality of measurements. Yeah, so that's the whole idea, is make it more accessible. Exactly.
So I think it's very nice work. So thanks for sharing.
Yeah, and there's others doing it too, and it's good that trying to spread it, because then you can also spread the ideas of the research community with instrument makers.
Yeah,
which is great as well.
Okay, I think we have Tom back.
Okay.
Yes, I'm not sure what happened. I think I clicked on the wrong thing. Let's see, I'll try and share my screen again. Let's see. Let's see. So, Sebastian, did you have an idea of why this video won't play?
Yeah, when you select the sharing, there is an option like optimize automatically. You need to like click there, go down to optimize for video and sound.
Okay. Let's see. I'm not sure if I can get this to work, but Mark, I can show you this next week when we chat.
Yeah, next week. What kind of measurements is it making when it goes through?
Dimensional measurements, so density, and then the long and cross grain resonant modes. And a newer version can do the twisting mode too. So just those three fundamentals for like a guitar plate, acoustic guitar plate.
Okay. Nice.
Yeah, it's really interesting that you're working on a similar thing.
Similar type of things, yeah. Yeah. Nice.
Super cool. Um,
Yeah.
Yeah. I guess we can chat more about it next week. I'm excited. Yeah.
The only thing you need for doing the sound synthesis is the bridge admittance of the instrument, no?
Yeah. I mean, yeah. So the bridge admittance of it's both instrument, the electric guitar here and the acoustic for the processing.
And actually, you make a feed to the first. I forgot the number of modes. 30 modes.
I think I was doing 50. You know, you choose on the quality of the fit you want. At some point in the high frequencies, you don't trust your measurement anymore, as it turns into noise. So generally, it's just approximated with some kind of general filter, or I think I was just doing like a single kind of high shelf filter to approximate the low modes. All the amplitudes would fit with like least squares, so it's fitting to what's there.
Okay. And have you used like results from simulations to create the sound?
I haven't yet, but I mean, in the same method, that's, you know, you could just as well, because it doesn't need a measurement. You just need the frequency, amplitude, and damping of the
And
modes.
damping. Yeah.
Yeah,
So,
because it's all parameterized by second order filters.
okay, so we could give you our results on the metamaterials guitar and you could make it sound.
Yeah, I could try. Yeah,
Okay.
and at some point, I need to, you know, this is all I need to actually write this as a C++ plugin, which then I can, like, you know, distribute. I just, you know, finding time to do a lot of things I need to do. But then, yeah, the idea is that, yeah, I could give that out. You can upload your modes, and then hear it.
That would be amazing. Really, really
Yeah,
cool.
and like, you know, it's never going to be perfect, but it can at least give you an idea, I think, is the idea, the point.
Yeah, I mean, and we cannot even make the air simulation because it's just like too time consuming for a master
Oh, okay.
thesis. But we
Yeah.
have the bridge admittance, so it will be like really nice to hear the difference.
To hear, yeah. Yeah, I mean, you can like there's lots of I think Woodhouse has a paper on just doing, you know, this kind of thing with simulations purely with like waveguide simulations and testing different um, parameters of like, you know, how much variance in the frequency or the damping that you can actually detect. I did a perceptual test. Um, I want something like on the perception of plucked string instruments or something. Um,
I don't remember it. Let me
but
make
then,
it.
yeah, yeah.
If you want
Actually,
to
I
share
can't
that.
remember yeah, I can't find. I'm sure I have it somewhere, but I'm not sure if I'll be able to find it right now. Yeah, plucked guitar transients comparison of measurements and synthesis. It was an
Okay.
acoustic. Can I put it in the chat? I think this is the one I'm thinking of. But so they're doing it with just fully synthesis. So I think they're just generating like string single plucks, from what I remember at least. But that, yeah, the thing that, you know, it's one thing to listen to single plucks, but to actually hear the, you know, a normal playing thing is different, and that's really hard
Yeah.
to do with just synthesis. Yeah.
Cool. Okay. So I think I will be sending you some FRFs soon.
Yeah, sure. I can. Yeah, that sounds because I haven't actually done it with synthesis, you know, generic ones yet. Even though it's capable of doing it, I just haven't done it yet.
Okay. Great. Any other questions? I think for the Italians it was a bit too late because they need dinner and stuff like that.
Yeah, yeah. The time
So
change isn't great.
it's difficult. But when you are in September, we can like do it again, probably live.
Okay. Yeah, that
Uh,
would be great.
yeah, and about that, I will come with news probably next week. I was a bit sick this one.
Ah,
So we probably have a place to have a little conference. So
awesome.
okay, thank everybody who came. I'm going to stop recording. Stop. And